Okay, there you go. Sanmitra, please take it away. Thanks.
Thanks, Sam. Thanks a lot for inviting me for this seminar series and talk. So, as the title suggests, it's quite a loaded title with so many terms going on, and each of the term has its own history and like meaning. So, I'll walk you through it. But let's first start with the basic motivation of why I'm talking. I mean, like I'm doing this type of work. So the basic motivation is over the last, I would say, decade or maybe couple of decades, we have enormous progress in actual hardware capabilities. Like we have got computers that can now simulate very complex physical processes. And I kind of highlight the simulation term here first. So we can, from starting from like the smallest particle to the cosmic microwave background, we can simulate very complex processes, right? And generally simulators are like this. We have some theory which with some with some parameters that we can tweak. There are some latent variables, and finally we have output of the simulators, and those output are kind of we treat as actual observation of the physical process. And basically there is a lot of work going on in designing or developing sample efficient techniques for inferring the joint posterior distribution of this type of simulator models. So my background is in the bit in the middle of that those images. That's epidemics. In epidemics we like to simulate very large scale models where we kind of track each individual out of millions. So we need methodology to do inference of all the unknown random variables of such complex simulator models. So today I'll specifically focus on something which we all know, that's the hidden Markov model. We can also call this state space models. So particularly we have some transition density from which we can sample the next state, and then we observe that state through some emission density or some noise process, observation process. And the goal is generally to infer the parameters of the transition and emission densities, as well as the hidden states of the process, right? So exactly, that's what I've written in this equation. This is basically the joint distribution of the sample path of the latent process as well as all the parameters. And now I'll introduce another term, which is implicit. I mean, like in my title, I use the word implicit. So by implicit, I mean that we are looking into special cases of hidden Markov model where these densities, the transition and the emission densities, we can generate sample from them, but we might not have the PDFs for them. So we cannot evaluate these densities, but we can generate samples from these densities. Either we cannot generate, either we do not have both F and G, that is both the transition and emission, or in a lot of cases, we might end up in a situation where we do not have the transition density, right? And these type of models fall in the general class of simulator-based models. So over the years, I guess for last decade, two standout algorithms that generally deal with these problems is the particle MCMC algorithm and the ABC method. ABC is not just an algorithm; it's just an approach, but we can devise various algorithms out of these two. One of the big, I would say, problem of using these algorithms in actual practice in some of the models I've shown in my first slide is that there's a lot of simulation that's required. And when we are dealing with very complex processes, simulation is computationally prohibitive. So that is one of the challenge in this type of implicit HMMs. All right. So obviously, ABC is immensely popular, especially in physics and computational biology, where people actually are using those sort of complex simulator models. And particularly, there is this variant of ABC that's called the ABC SMC algorithm that is extremely popular. And the general idea is you use kind of a simulated data. So you simulate from your model, and then rather than computing the likelihood, you replace that with a distance function between your simulated data and true data. And when you have complex data, then you can use summary. And if you have the the summary is chosen as the sufficient statistic, then obviously you can actually get the true posterior given that you have a tolerance that's 0. So in practice, we never reach this situation. Our summary statistics are never sufficient. We never are able to reach a 0 tolerance situation. So basically, we'll be never recovering the true posterior. But the nice thing about ABC is that there's a lot of theoretical work that has been done mostly recently, and we have some good understanding of some of the key issues in ABC, for example, concentration rate and all this stuff. And I would say the problem of ABC, or the limitation, is that it requires huge simulations, obviously, because it is dependent on generating simulations, right? So obviously, for some models, if the model is not that computationally expensive, maybe ABC is a good algorithm. It's a good strategy. But for kind of models that we are envisaging in the future, like simulating each human being of this country to model an epidemic, and there are models like that. For those type of situations, ABC won't work, right? And then there are additional difficulties, like there are some parameters, algorithmic parameters, like the tolerance or the sufficient stat or the summary statistics. And the problem is that there are very nice work on how you kind of choose this stuff. But if you make mistake, or if the choice is not done correctly, then obviously it will hurt the sample efficiency of it. So basically, you will end up with humongous simulation. So today's topic, I would guess, where I am quite interested in this machine learning approach, especially deep learning approach that's been kind of now used to do likelihood-free inference. And generally, these can be called as a neural likelihood-free inference, because at the end we are using some neural network to do this likelihood-free inference. So one way of doing is that we generate simulations from the model. That is, we simulate parameters from the prior, and we then use the simulator, the HMM, to generate the data. And then we use some sort of neural conditional density estimator. Specifically, we can use normalizing flow that we kind of talked a lot about in the variational inference masterclass, but you can use other conditional density estimator as well. And once you train a density estimator on the simulated samples, then you can use that density estimator on a new instance of a data set to directly sample theta. Obviously, this is just a rough summary of how this is done. There are obviously some other details, like obviously you can generate those samples, but they might fall outside the support of the prior. So some sort of corrections are done, but the general meat and potato idea is this, that you feed a conditional density estimator to samples simulated from your prior and the model, and then use that conditional density estimator to generate your posterior sample. So this is one idea. Another idea is that rather than training a conditional density for the posterior directly, let's train a conditional density estimator to emulate the likelihood, right? So we can emulate a density, we do the same procedure, generate the parameter samples as well as the data from our model and prior, and then use some sort of conditional density estimator to emulate or approximate the likelihood, then plug that density estimator inside your MCMC routine, right? And then it's just basically how we do MCMC. So this is another approach, and I call this approach, this approach is called neural likelihood estimation, and the earlier one was neural posterior estimation. There is one third technique. This is basically kind of approximating the likelihood ratio, right? So the idea is, again, generate a training data set from samples from your prior and your model output, and then you kind of train a classifier. And there was some work where it was shown that if you train a probabilistic classifier to kind of distinguish between a reference parameter and any other parameter value, then that optimal decision function of the probabilistic classifier gives you the likelihood ratio. And so I think Kyle Cramner's work, which I've cited, he kind of first introduced this idea in 2015. And so this way you can actually approximate the likelihood ratio, and it's still neural because obviously this technique is used in where you kind of use a neural network based classifier to learn the ratio. So obviously the neural network is still there, but interestingly for this particular technique you can use any other classifier, but obviously generally neural network based classifiers are used. And once you have the likelihood ratio, you can then again kind of plug that in your MCMC acceptance step, and then you can run your MCMC using that. So this technique is called neural likelihood ratio estimation. Now, why I got interested in this method, because there was some work by Luckman, I think last year, and some work going on where it was shown that at least on empirical study on a wide class of models, that these neural likelihood free inference methods, all these methods are like 1,000 times more sample efficient than ABC. And that's a huge thing for like simulator models where we are interested in like really fast inference for complex models. The sample efficiency reduction is enormous. And in a lot of those studies, it was shown that actually these NLFI kind of retrieve, or they produce approximation that is more close to the true posteriors, right? So that's why not just me, a lot of people got interested in these type of methods, right? And generally one of the other interesting observation from those studies were that they are not that finicky to all these like neural network fiddling. So you can use they are kind of robust to your architecture choice, how many hidden layers, how many neurons. You don't have to fiddle a lot. Generally, kind of these models hold across different applications. So that was also encouraging. And generally, these methods were then developed to work sequentially, taking ideas and inspiration from sequential design and active learning. Is that you start with a handful of simulation from the prior, do a single round of inference, get your posterior. Of course, this posterior won't be that good because you're using a very tiny, maybe 1,000 samples, right? And then you kind of sequentially refine this estimate. And obviously, you can refine these for number of rounds, 20, 30 rounds. It's very similar to active learning, basically. One of the important things is that from the second round onwards, you are no longer generating your data set from the prior. So that's a problem, right? Because you need to generate data from your prior. Otherwise, your posteriors are not consistent. So obviously, you need some sort of correction. And I mean, like the work that I've cited are some example, but there have been many work on like how exactly you do that correction, right? So there have been many work of doing that correction, but this even makes it further sample efficiency. So like you're looking at ABC taking for a model like 10 million simulations, and you're getting kind of similar or slightly better result using say 10,000 simulations, which was insane, right? And that means that now we can actually do inference for like cosmic microwave background or like individual epidemics or all these sort of crazy models that we cannot think of doing inference using existing methods. Okay, so I have just one slide for normalizing flow for conditional density estimation, because I think we have gone over this normalizing flow in detail in our master class. So like you can all check out the videos and lecture materials from there. The basic idea here is very simple. We start with a very simple random variable, a standard Gaussian random variable Z0. Then we pass it through a series of bijection, and we choose how many bijections we want. And we take the output of the last bijection and take that as our target variable, right? And each bijection has two inputs. One input is the random variable at the earlier layer, but it also has additional input, that is the conditioning variable. And if we do that, we end up with the density of the conditional density. So I mean, like this was suggested at the initial normalizing flow papers. And so the idea is very simple. Again, generate samples from your prior or the joint density. I mean, like samples like you generate by ancestral sampling, that you generate theta from your prior, and then from your likelihood density, you generate your data. Then you maximize the total likelihood using normal gradient descent. And there was some recent work which kind of finds equivalency between likelihood maximization for this type of model with kind of Kullback-Leibler divergence of the approximation. So there's some work. I won't go much into that, but yeah, you can check out this type of approaches or work that's there. And of course, there are a lot of intuitions about the idea that these are universal density approximation, that given enough flexibility in your H function or in your bijection, if you give a sufficiently flexible function as a bijection, then you can approximate any density, which comes from like the universal function approximation of neural network. One key ingredient here is that taking the Jacobian determinant is expensive. So like the main research here is how do you kind of design this bijection so that you have a lower triangular Jacobian, right? So in that way, you can easily evaluate the density without too much computation. And note, sorry. Okay, and note that here I'm showing that estimation of the posterior theta given y, but you can use basically the same thing to do it other way, that is y given theta. All right. Now, limitations of these methods when we bring the joint posterior, because so far I was just talking about theta. Now, obviously, in a lot of simulator models and in general physical processes, maybe we have 10, 20 parameters, 5 parameters. These are easy to deal with using smallish neural networks, right? But as soon as we pop that sample path there, then there is trouble. Even for like the simplest like stochastic volatility model, you can have like a kind of very high dimensional sample path. Now, obviously, the brute force idea is take the neural posterior estimation idea and kind of try to target this concatenated large vector, which is sample path and the parameter. Now, the problem is, if you want to do that efficiently using a neural network, then you have to bake in some sort of inductive bias in your network architecture, right? All the success of deep learning is basically we kind of put prior knowledge in the architecture, right? The convolution neural network, the LSTM, and the transformer, they all have these inductive biases. But unless you give explicit inductive biases to this network, you'd end up requiring a huge number of simulations. So this is basically a general idea, and so obviously it's infeasible. I won't be showing any simulations for or results for this, but this is like very easy to understand, and like generally this is a bad idea. The next idea is, okay, forget about doing the posterior directly. Why not we go and fit the or emulate the likelihood? That can surely be done. Maybe we can kind of use factorization of the likelihood and learn that way. But here is a problem, because when you are dealing with implicit model, you might not have the transition density. And as so your joint prior over your sample path and theta, that might be intractable for many models, or to be honest, most models. As soon as that happens, then you are in trouble designing a good proposal for the sample path. And basically, this problem is basically going back to 1980. Before SMC, right? That the reason this is difficult, that's why we have SMC and particle MCMC, all these methods, right? Because it is extremely difficult to design that sort of proposal when you have intractability in your like joint density, and the only way you can do it is you use the prior as your proposal, and then you'll never have convergence. So obviously the best way to deal with this type of MCMC is using particle MCMC. But remember, as soon as you go to particle MCMC, you are back into high simulation, lower sample efficiency, because for each parameter sample, you have to run a particle filter. For complex models, you need a large particle size maybe, and then basically it's kind of defeats the purpose of doing NLFI. And remember, this is the same problem we'll have if you want to do likelihood ratio estimate. So basically, we are stuck here for the joint density. Now, obviously, a question should be, I don't care about the hidden state. I just want the posterior. Those are the scientifically very relevant parameters. Now, obviously, Daniela in the audience would disagree because like she's been an epidemiologist. Obviously, we are interested in learning the hidden state, for example, finding out the reproduction number, right? So we need the hidden state. But let's forget epidemiology. For many other, maybe in physics, maybe in particle physics, maybe we don't care about all the scattered particles from the collider. So we just want the marginal posterior. Now here is a problem I have for that question. Can we really ignore the joint distribution? Now, in all practical purposes, when we are kind of designing a new model, a very complex model, which is expensive to simulate, we generally kind of see the assessment of the model or just do the goodness of fit assessment, at least in the Bayesian realm, using the posterior predictive data. And here the posterior predictive data, I mean like the replicated data of like Gelman. So basically you want to see like if you generate from your predictive distribution, then you generate data close to what you have observed already, right? So this is what we always do, kind of to look at the goodness of fit. This is not the only way to check goodness of fit, but this is a very important, like especially when you're designing a new model, right? I want to model some sort of nonlinear dynamics. I really want to see how I'm covering that nonlinearity, how I'm generating my trajectories, right? Now here is the problem. You only have to do that. You need the joint distribution, right? And the problem with doing just the marginal is that using NLFI, that you have no access to X. Now I like to be very specific here. All classical pseudo-marginal methods always generates the X, even if you don't care about it. Like you want the marginal of theta, but whatever the algorithm is there, they all generate the X in the process, including ABC. It's a unique thing of NLFI methods that you do not generate or draw samples of X from the posterior. You only have X samples from your prior for creating the training data set. So the only option is this equation number 7. And this is basically a wrong factorization of the joint density, right? Because your sample path are no longer correctly constrained by the data. Now, this is a severe problem because this will lead to incorrect assessment of the goodness of fit, right? And so you can think of like a good example, like a thought experiment would be, right? Think of like your transition density to be multimodal, right? Now you can have data associated with one mode. You do your estimation of theta and everything, but because you're not constraining X correctly, your posterior predictive will be from both the modes. So you'll have huge uncertainty. So you'll incorrectly kind of predict the uncertainty of your posterior predictive distribution, right? So these are problems. So how to deal with it? NLFI methods have shown earlier that they have problems of jointly targeting. And so till now, this is basically the background setup of my work. So I want to do this using an idea inspired by variational inference. Of course, getting the actual joint density is impossible, but can we get some sort of mean field approximation? Okay, so here is the idea. We decompose the joint density using the standard like factorization, right? Now, if you look at these factors, P theta given Y, we can use NLFI methods for that. Now, once we have this, then for each sample of theta, we can draw a sample from the posterior of X, right? So the idea is if we can separately infer the marginal posterior of the parameter and then the marginal posterior of the joint sample path, then we have kind of samples from both this distribution, and these samples would kind of give a rough approximation to the joint distribution, and maybe most importantly, improve our posterior predictive assessment, right? Now, of course, how do you do this inference? Because as I said, like even for simple models, this X can be very large. So even if we got rid of theta, if targeting X is not easy, right? Using a constraint simulation budget, which is a constraint we all have throughout these models, right? So obviously one possibility, use SMC, right? We know that even if the potential, the emission density is not available in addition to AF, we can still use ABC, some newer forms of ABC like alive particle filtering, which is using ABC inside of an SMC algorithm, or a very new work, which I think Denise was a co-author, so which is based on the generalized Bayesian inference kind of framework. And obviously, as soon as G becomes available, we can try out the bootstrap particle filter. Now, obviously, if your model is computationally tractable, or you can afford to do so, end of story. There's no point of going through my talk anymore, right? But I think that's not always feasible, because you need, remember, to do the posterior predictive approximation of the posterior predictive integral, you need a number of theta samples, and then for each theta samples, you need to run a particle filter, right, with number of particles. So take an example like I have 1,000 theta samples to get a good posterior predictive density estimation, and then I'm running a particle filter with maybe 100 samples. That goes to 100,000 simulations. Remember, I was telling that a lot of times 10,000 simulation would be enough for just NLFI to find theta. So again, you can end up with using substantially more simulations just to doing this filtering step at the end. So I mean, like, we want something even better, right? Ideally, I want to spend no more simulation than what has been already spent in NLFI to get the estimate of the states. And this I try to do it using normalizing flows. All right, so coming back to the idea of mean field inspired approximation. So the first thing I want to do is that if I look at the last time point of the HMM, the hidden state, we know that that's independent of everything else except its corresponding output, y t minus 1, and just the sample point before it. So if you take those two variables, then you can block all path leading to that thing. So obviously for the last sample point, we have this density. Now here comes the mean field approximation. For each of the remaining sample points, we know because of the Markov property that given this triplet, one sample point in future, one sample point in past, current output, we have a conditional independence out of everything. Now, the mean field and basically a lossy approximation is that I'll throw away the future sample point. As soon as I do that, then I can do kind of a lossy mean field approximation of just taking products of this density. So this is basically the approximation, the first approximation that I want to do. Now, why I want to do this approximation? Because as soon as I do that, then rather than fitting a normalizing flow to this high dimensional X, now my task is cut out to fit a normalizing flow to each of these potential. And remember, because it's HMM, this distribution is same for each time point, right? And so basically, we are again back into the general scenario where normalizing flows are used in NLFI, and we can deal with that, right? So here is the idea. We emulate.
Let's get a question, please, Sanmitra.
Yeah, go ahead.
So is the assumption from the start that X given theta is a hidden Markov model, or?
Yeah.
Because
Yeah.
is it not the case that this decomposition is exactly true? Or
Um,
no, okay, no, I'm
no,
thinking
because
one.
if, sorry, I should have drawn like the H. You just think of like any intermediate step, then it has two arms, left, right, and one down, right? If you block all of them, then it gets. I remember a paper by Pierre Jacob where he drew this beautiful diagram of explaining this conditional independence. But yeah, in the Chopin book also.
Okay.
Okay, so I'll go ahead. Yeah, so we now emulate this incremental density, incremental posterior, using a neural density estimator. And then we can approximate the posterior predictive as follows. That's basically, we draw, first we start with the initial point, draw the next one, and then we go ahead recursively. And I call this idea, or this density estimator, the incremental density estimator. Now, anyone among you who has been a fan of SMC would have immediately noticed that this density is the famous optimal importance density for a SMC algorithm, right? But here I kind of come at it in a from a different motivation. Yeah. Okay. So how do we train it? So this is how we do. We start from, can you see my mouse? Yeah. So we start from the prior, we generate a theta, one sample, simulate the HMM. You have the output trajectory, you have the hidden trajectory. Now you start chopping off these triplets in such a way that your this point your target, and these two would be your conditioning variable, and this gives one training example. Do repeat that, right? And then you generate a very large training set, even if your time series is not that long, right? So that's how you generate a large training set. And then obviously, as I have shown you, you can fit any normalizing flows based on that training set. So I'll come to that in a minute. And once you have generated the training set, you have fit your normalizing flow, then this is basically the graphical model. You generate your simple random variable, you take your data point at time t, your parameters coming from your posterior, and the latent state on the past sample of the latent state, use your IDA to generate the next time point. And then you think of like just recursively drawing it over the time factorial graph. Yeah. So that's basically the idea. Here, I have used a masked autoregressive flow as the normalizing flow. The basic idea is absolutely similar to the normalized conditional density estimator I've shown you. Again, we start with a simple variable and we pass it through some bijections. The only interesting thing is these bijections are autoregressive bijections, which will give us that lower triangular Jacobian. And we are now conditioning, rather than just YT, this triplet. That is the past sample point, the current observation, and the parameters. And one very efficient and brilliant way to kind of do, or I mean, like, if you want to do an autoregressive neural network in a naive way, that really means you have to do a lot of computation. So I think Ian Murray's group came up with this beautiful idea of like a masking idea to kind of do these autoregressive functions in one pass. So it's computationally quite, I would say, lightweight. And obviously, you use the change of variable formula to kind of find the conditional density, and then you use maximum likelihood to fit it. So that's basically the main idea. All right. So it's a summary of the method of drawing samples of both the latent state and the parameters. First, generate your simulated data and use any chosen NLFI method, ratio estimator, posterior estimator, likelihood estimation, to draw samples of theta. And interestingly, you don't need any more simulation. Just take the simulations generated in the NLFI, just take a subset and parallelly train the IDE, right? Then once you have the IDE and you already have theta drawn from your NLFI approximation, you just use the IDE to draw X, right? So the nice thing is exactly what my motivation was, that I don't want to spend any extra simulation. This can be done. And generally in all my methods, all my experiments, what I do is like I use a sequential NLFI, that I do multiple rounds of NLFI and I take the first round's simulation to train the IDE. So that's basically the summary of the algorithm. So coming to evaluation. So I have done the evaluation in two phases. In the first phase, my main idea is the basic idea of figuring out the posterior predictive distribution correctly. For this, I have chosen two biological HMMs, which have interactable transition densities. So first we will check this out. Once we have done this, then we will kind of look into more closely the filtering performance of this thing in the context of like classical filtering application, right? That was not initially my motivation, because my whole motivation was to get the posterior predictive density more accurately. But obviously now we have a way to kind of approximate a time series. So why not just throw it in the ring with the heavyweights of SMC and see how it fares, right? So this is the second set of experiment. All right. So what we are comparing for the posterior predictive testing is that the first strategy, you get your P theta of Y given by NLFI, then you run SMC. And this is the gold standard, because SMC given enough particles is going to get the true posterior of X. And so this is the gold standard thing. The second approach is basically what we are only left with current NLFI methods, is that what I call prior dynamics. Is basically you kind of simulate X from your prior and then generate the posterior prediction. The third approach, I throw in the ring the ABC SMC algorithm. I do it because ABC SMC algorithm, like any other ABC algorithm, they generate jointly the state as well as the parameter. The only issue with the ABC SMC that I found is that the whole of all the tricks of the SMC part that improves the estimate of theta, but within the ABC SMC, the X is still kind of sampled by basically drawing from the prior. But why I wanted to include this, because this is the like 9 out of 10 people working on simulators right now in any lab around the world would be using this algorithm. And most of the time, or in many situations, they use this algorithm on dynamical systems model, which are HMMs. And that's what the posterior predictive you will have. And finally, the ID. And to approximate all the integrals, I'm just using 500 samples of X, and sorry, this should be theta. So X and theta, 500 samples to kind of do a Monte Carlo quadrature for all these integrals. So that means for each theta, I have to run a particle filter. So basically, I have to run SMC 500 times. So how do we evaluate correctly? Because the problem is that the posterior predictive is also dependent on theta as well as X. So we are kind of tweaking in two different angles, and we want to kind of isolate the role of X estimate rather than the theta, because we know how NLFI works for theta. So to rule out the possibility of theta influencing the outputs, what I've done for at least these three methods is just I've used the same theta samples generated by the same NLFI method when I'm comparing SMC, prior dynamics, and ID. I cannot do that for ABC, but what I can do is that we know a lot of literature there is a lot of literature comparing ABC SMC with NLFI. So we can use fixed simulation budgets. We use as many simulation as possible for ABC SMC, practically feasible, so that maybe the theta estimates for NLFI and ABC comes as close as possible, right? So that's what I've done. And I have used sequential version of the likelihood estimation and the ratio estimation. And I have omitted using the sequential posterior estimation because there was a recent paper which showed that you can prove that NRE, the ratio estimation, and posterior estimation are equivalent under like under the framework of contrastive learning. But like the idea basically is that we using likelihood and ratio estimation, we can generally cover the whole ambit of NLFI methods. Right? And we have used summary statistics for ABC as well as SNLE, SRE for the latter to estimate theta and for the former to estimate the joint, because that's what's done in literature. As I said, to rule out the differences, we used fixed budget of simulation because ABC simulates them jointly, and this is simulating on this is estimating only theta. So basically, we kind of we had to figure out what would be enough so that both of them comes to at least the same ballpark, right? And these budgets were based on like previous studies, and we are pretty sure that whatever the differences in this quantity, the posterior predictive between the methods is mainly attributed due to the quality of X estimates. We have taken at most care to kind of make sure that theta is not influencing. Obviously, there would be some differences. I cannot control that. Okay, so the models. The first model is these models are used like in loads of paper on this type of work. First is the stochastic Lotka-Volterra model, and the second one is a autoregulatory model, gene network model. And both of these are basically Markov jump process. The dynamics is governed by Markov jump process. And that means we cannot evaluate the transition density. The PDF is not available, right? Because for that, we have to solve an intractable partial differential equation. So complicated stochastics. But obviously, we can use the Gillespie sampler to simulate XT exactly. So this is kind of the model territory. Obviously, it's a very simple benchmark toy model, but obviously these are good enough to play with, right? And we have chosen the likelihood density or the emission density to just Gaussian density so that we can use bootstrap SMC. Otherwise, we had to compare all sorts of SMC. But we know that when G is given, bootstrap SMC will perform better than the ABC alternatives of SMC, obviously. And we obtain the summary statistics by subsampling the time series by a factor of 5. And we did some subsampling of the time series to kind of preserve the morphology. So for example, the Lotka-Volterra produce limit cycle behavior, that is oscillatory dynamics. So even if you take summary, we wanted to have that same oscillation there. So that's what we have used for subsampling. Okay, so there's a lot of setup because we are using so many things here. So we use the bootstrap particle filter, and I think I used residual resampling. Used 1,000 particles, and this was based on like earlier work by Golightly, and I mean like so I think that would be 2011 paper. But there was a series of paper by Andrew Golightly looking into these models using particle MCMC type of approaches, and generally 1,000 particles he found like is good enough. So of course the total cost now would be, as you can see, 50,000, right? So no, I'm sorry, I said 50,000. Yeah, more than that. Yeah, so quite a bit, right? And for the ABC SMC, I again kind of, to be as consistent as possible, use 1,000 particles, some adaptive tolerance sequence, which is like very popular in ABC literature, and I use kind of what is called this locally optimal covariance to kind of jitter the theta particles within SMC. And I restricted the total simulations to 10 million. I think that this is something I've seen in the earlier NLFI paper. I mean, like I can wait till infinity to kind of like, I can use like more, but I think 10 million simulations is kind of good enough, right? Okay. For the SNLE, remember, I need to do a conditional density estimator for the likelihood. We use the same thing, that MAF, and I use like 5 bijections, and each of the bijection is a MADE architecture, which has 2 hidden layers and 50 units with ReLU nonlinearity. For SRE, that is ratio estimation, I use the residual ResNet architecture, not very complicated, simple ResNet architecture, so that the derivatives flow well. And again, using two hidden layers and similar kind of units and non-linearities. Something I've kept consistent for both is that I've used 30 sequential rounds, 5,000 examples in the first round, and 1,000 examples in the sequential round. So you can see that my total simulation budget for NLFI, including the IDE, is less than 40,000. Compare that with the SMC cost and the ABC SMC cost, right? And obviously the general tricks from deep learning use Adam, early stopping to avoid overfitting. This is quite important. I mean, if I remove that, then you can see overfitting. And I use slice sampler for MCMC, which I don't think is the best idea. We can use better things for MCMC, and obviously we can use like HMC as well, because all these density estimators, they are differentiable themselves. But this is what I kind of people use in NLFI somehow. I think because the first NLFI paper came from Ian Murray's group, so so the slice sampler has slipped to, to there. So I kind of kept the tradition and used that. For the ID, here's the most, I think the most interesting thing is that I use the same map, same optimization setting, same thing. I use the exact same map for the likelihood density and for the ID. Changed nothing. Same number, less, same thing. And obviously the first round simulations are used to train. And so the metric of evaluation, what I figured out, or this is what I think, is that at the end of the day, we want to find closeness between two distributions. But generally, people use different things for time series outputs. But at the end, this phase of evaluation, I am interested in to learn how close my competing approaches are to my gold standard estimate. And closeness in the space of distribution can be done well with any integral probability metric. I've chosen MMD because I have a working code that I use all the time, right? So what I did was find the posterior predictive using SMC, compare that with the three other approach, and then sum them over the entire path length. And because MMD square is positive, so obviously the minimum MMD among these three methods, ID, Priordine, and efficiency, means that would be closest to the gold standard. So that's the idea. So here is the table. So there's two tables. In the first, I'm using SNLE to get theta given y, while I'm using SMC ID and prior dynamics. And in the second table, I am getting the theta given y using SRE method for these three things. And here, see, there is a huge difference. Like IDs for both the models is as producing much closer MMD to. Obviously, I expect this to be bad, but look at this ABC SMC, and I've run this model like 100 times because I couldn't believe what's going on. That ABC SMC is producing worse than generating from the prior. But I finally figured out what's going on, and then I'll come back to that. And here, what I'm doing is that in this table is that I have generated 10 simulated data set, and all these MMDs are summarized based on 10 alternative data sets. So clearly from these two models, and these are quite, I mean, like simple models, but the prokaryotic one is tricky. It has some identifiability issues, and like this model is like the main model of many classic famous papers. So I think getting good performance on this is good enough. So here is like the parameter estimates, again summarized across the data sets. And again, I have borrowed from like the NLFI literature, where kind of you compare the kind of goodness of fit using, so you have like a 8-dimensional or 10-dimensional parameter, fit a mixture of Gaussian to that parameter estimate samples, and then find the log probability of the actual ground truth parameter under that mixture of Gaussian. So this is I'm not a big fan of this method, but this is what is used in all NLFI papers, so I had to stick to it. But the main idea here is for Lotka Volterra, pretty similar, all of these. clearly the difference is in X. Even for the prokaryotic, I mean, like, there is not a night and day difference. I mean, like, obviously I've tried other things, but the ABC SMC is inefficient. Unless I give like 10 to the power 15 simulations, I cannot take it higher. But still, I mean, like, these estimates are not that different, to be honest. Here is the estimates of the hidden states. And here we can see that it's all about getting the hidden state correctly. And for the Lotka-Volterra, I'm just plotting here one component. Solid lines are the mean and the broken lines are the credible intervals. Here is a question: can you distinguish between SMC and ID? So they are almost indistinguishable, to be honest. I mean, like, for both this one as well as this one. And once I had these results fast, and I was quite startled by this result. And then I actually tried on other models, and they hold on different models as well. But for this talk, I'm showing these two models. They're pretty close. And for forget the prior dynamics and ABC, but for the SMC, you are using 1000 times 500 simulations. Doesn't matter if you do parallelization, because I can do the same for the NLFI. And ID, you are using like how much? 34,000 simulation. 34,000 compared to like the SMC burden. So obviously this makes sense for complex models, right? Now here's a problem, that summary statistics for the SMC, ID, and the prior dynamics, where because for all these three methods I'm using the same parameter estimates. So it doesn't matter if I use summary, because I'm using the same theta to estimate the posterior predictive for all these three algorithms. However, when I'm comparing ABC to all these other things, the summary is used to estimate both the parameters as well as the hidden states, which is not the case for others. For all SMC, we are working on full data for X. For ID also, we are working full data for X. So obviously there is a little bit of problem when we are using ABC SMC. Now I checked it with the Lotka-Volterra model, doesn't matter at all, because all it needs to see is the limit cycle. As even if I'm using like subsample time series, as soon as it gets the limit cycle, it gives the same output. But for the prokaryotic model, this might affect a little bit. So what is the workaround? So the nice thing about all the ratio estimation is that we can actually learn the summary on the fly. So we are training a classifier, right, to learn the ratio, likelihood ratio, but we can augment that classifier with any sort of deep neural network to learn some sort of summary. I've used the most simple one, which is like a LSTM module. I'm not going into details of it, but it's a very simple technique used in like lots of any time series work, right? You can, I've recently tried with other things. So use any sort of simple neural network architecture for time series to get the summary. Add it with ResNet and learn the summary. I have chosen the summary in such a way that I have like eight dimensional summary statistics, which is learned on the fly. Now you cannot do that with SNLE, the likelihood estimation, because the target variable is the data. So you cannot directly use the summary statistics. But since both SNLE and SRE were giving me similar, I mean, like almost very similar estimates of theta, so I dropped out SNLE out of the comparison. And ABC SMC algorithm particularly was originally designed for dynamical systems and was designed to work on full data. So rather than taking distance between summaries, take a Euclidean distance between the whole time series. That's what I've done. So now I repeat the entire thing for at least the prokaryotic model, which is the more trickier model, with summary, without using summary. So the and just using SRE. So this row, W sum is basically the earlier result with summary, and no sum is basically using no summary. And again, ID is like minimal difference between ID. The only difference I see is that now, because I'm giving the full data, at least the ABC is doing better than the prior dynamic. which I expect. So not giving the full data, ABC was doing worse than the prior dynamics for this model. For the other model, Lotka Volterra didn't matter. But for this model, it slightly improves, right? But still ID is like, I mean, like our main conclusion still holds. And here is the comparison. The left plot is using summary statistics. The right plot is where ABC is not using the full data. I mean, like, okay, it gets a little bit better than sampling from the prior, but I mean, like, not a big deal, right? But I still did this sanity check. I mean, like, to see. All right, so going to the next phase of model, and this is the last experiment. So the idea here is that use a nonlinear Gaussian state space model. For this type of models, we can exactly calculate this distribution, right? These are Gaussian densities. This is nonlinear, so there is nonlinearity, but we can calculate exactly the true posterior here. And to make things interesting, what I did was I tried out 10-dimensional state space, and I tried longer time series, that is 500 time points, which is good enough. I have recently, like last evening, I've tried till 30-dimensional, and all the results I'll show they hold for till even 30-dimensional state space. But the 10-dimensional is one what I have here for the talk. And I have chosen two noise regimes. One is where the dynamics noise is lower than the observation noise. So you can call this like low signal, high signal to noise, or and the other is you have the same than noise for both the dynamics. And here we are only interested in the filtering performance, so we consider a fixed theta. So think of like this theta has vanished now. It's just the classic filtering arena. Now, as I said, the ID is a lossy mean field approximation, but can we do a little better? So what I was thinking about recently is that the ID concept is very general. So I mean, like all the intermediate points of the HMM, they have this distribution, but I can approximate this distribution building an ID for this distribution. Same technique, same steps, same way of learning, generating hidden states and training data set and everything. And then just like do a poor man's SMC. So basically mimic importance sampling. That is, here ideally the importance weight should be the actual density P of this, given this the ID that I have shown so far, that being the importance density. But since normalizing flows can get very close to true one, why not do this as an importance density, and then kind of correct these samples using these important ways. So I call this strategy ID imp, importance. Okay, so here is the setup. Firstly, there's two types of bootstrap SMC, one with 500 particles, general operating scenario. I want to do bootstrap with small particles, and then actually increasing, going to larger particles, 5,000 particles. Now remember, I told you that this distribution that is basically the optimal importance distribution. And so because this is now tractable for a nonlinear Gaussian model, that's why we can run what is known as the guided SMC or the guided particle filter. If you following Nicolas Chopin's book, I guess. Yeah. So I've run this again using 500 and 5,000 particles. Then why not just draw from this? Forget everything. I know this is tractable. Draw from this, because at the end of the day, ID is going to mimic this thing's behavior. So let's see how they compare. And finally, ID importance sampling should mimic the behavior of the SMC, because hopefully they would be more closer to the true distribution. And I've used two metrics. Generally, these are used for this type of studies because I think all of the results should be close, nearby. So one is basically to get the model fit is the MSE of the actual hidden states and the empirical coverage. And what I've done is basically I've summarized these values across the state dimension to get one single number. This is following some more recent work on this type of thing. So first, the low noise dynamic. All right. So here, what interestingly, firstly, if you have the true importance or the true optimal density, then obviously you see that it's better than doing bootstrap, right? Even with 5,000, this is exactly what we expect. The guided SMC should beat everything else. That's what it's doing. Interestingly, the ID, I mean, like the ID is not falling back to the bootstrap level, but it's closer to kind of the, I would say, the true IP level, whereas the ID importance sampling is more closer to the bootstrap particle filter, which is so this, without the importance sample, this should be ideally exactly like that, and this should exactly be like that. And so kind of see they are mimicking the behavior, which is assuring. And if I go and look at the empirical coverage, again we see that same thing, that ID is better than everything else because the actual quantity is better than everything else. So that means the normalizing flow is doing a very good approximation of the true thing. But the importance distribution is also working. That means I'm also, so going back to this thing, this approximation is also working quite well, hopefully. So this is behaving similar to the SMC stuff. So this is encouraging. Now the high noise dynamics. Now you have noticed here, if you have noticed that the bootstrap SMC is gone, it doesn't work. If you have like this time, this you can think of these as a like a highly informative, because you have a high noise dynamics, and then you have the similar noise in your output. So you can think of these as like a highly informative sort of things, and generally, and the bootstrap like completely fails, bombed. So the guided particle filter here is doing well. True, I see like the true IP kind of very near to the, for at least in terms of MSE, to the guided one. ID close to that. Here, surprisingly, the ID with importance sampling is beating everything else. Even like a guided particle filter with 5,000 particles, which is like quite interesting. And we see same thing for the coverage, because I mean, like the ID importance sampling is still the highest among everything, right? So that means that firstly, this is not a simple dynamic problem. This model, I think, have been used in a lot of papers. So this is not very simple. You have like tricky noise, high dimensional state space, long time series, and still the ID as well as the importance corrected one is still holding on. So that's encouraging. But remember, I have used only 500 simulations of the model to train the ID, and the same 500 to train the importance sampling ID. So here you're using 5,000 for the guided SMC, 5,000 simulation, versus you're using 500 simulation here. With 500 simulation, the bootstrap doesn't even work. So that's quite encouraging, right? But challenges, obviously. We have no theoretical understanding of anything we are doing, to be honest, and that scares me. But obviously, we cannot wait. But I think this, I kind of work on this stuff to kind of not, I would say, kind of a plea to like theoreticians, mathematicians to take a look at this. I mean, like if you go into like lots of statistics department, you'll see so many people working day and night on theoretical properties of ABC. Can we stop that? Can we really work on this, right? Because we see this is useful, and this is my humble request to all my colleagues and friends who I know are good at looking into theoretical properties. This is interesting, have a look. But I think we want those theories, not like just because we want a theoretical backup. No, because I think if we know the theory, we'll improve it. That 10,000 would might go to 2,000 if we know a little bit of theory. And there are some interesting results. I think empirically people have tried out some posterior concentrations and all that, and they are in the right ballpark. But yeah, obviously, maybe here maybe I'm very excited by Badre's work. on like Oracle inequalities, maybe that would be the right place to start at looking into this, right? And okay, so that's one thing. Other thing is obviously if theta is estimated incorrectly, the ID would have trouble, right? Even if you do your simulations and blah blah blah, if your theta is wrong, you will lead to wrong x estimates and you'll have wrong posterior predictive. So that has to be taken into consideration. But here is a good thing. Maybe you're doing ABC SMC or some sort of ABC method. You can still plug the ID after your ABC. You can use that. And I think the biggest challenge is that I mean like this wouldn't work if there is model misspecification. Here I'm expecting that the simulator is the reality. The more complex that phenomena becomes, the more we walk away from reality and there is more model misspecification. I don't know how to deal with it right now, right? And the second thing is that without the important sampling, I think the pure ID thing will work very poorly for regime switching model because we are throwing that future point. So if there is a shock or something, it would lead to problematic results. But maybe the important sampling might improve it. I don't know. So because I've tried it on like all sorts of toy models, and generally, like obviously more rigorous empirical tests need to be done, and obviously good diagnostics. That's I think that's the most important bit that is challenged, to figure out good diagnostic. Again, that goes back to my theory point, obviously. So that's why we really need theory urgently, so that we can have some good diagnostics. That's it. All right. Here are the collaborators, Daniela and Paul. So thank you.